As systems manage higher volumes of complex data, developers increasingly turn to index data structures to enhance performance in locating a given data object. Used properly, indexes can boost speed logarithmically beyond that of a linear data search. However, when indexing is contemplated, the first and often the only index to be considered is likely to be the B tree, as Chris just mentioned. Out of all the indexes that can order records in database management systems, only B trees are offered universally. And often they're the only index offered, and there's no denying B trees' efficiency for basic database search operations like exact match, prefix, and range searches. But these plain vanilla indexes are often a poor fit for certain data and access patterns, such as IP routing, geospatial searching, and in-memory database systems. Therefore, it pays for a programmer to understand a wider variety of indexes that may at first glance appear more exotic. Diverse index types enable important design trade-offs involving search performance, memory consumption, and update performance, and some indexes offer distinct advantages for certain application categories. This presentation is going to examine less well-known indexes that can be a good fit for certain application needs. The B tree is the most popular data structure used in database and file systems and provides efficient, general-purpose lookup and sorted retrieval of entries for a large volume of data. We'll look at R trees for geospatial indexing, which is common in GPS and navigation type systems. We'll examine the Patricia tree for router and telephone directory searches. This is also known as a longest prefix match index. T trees are appropriate for all in-memory data storage and access. Whereas the design goal of a B tree is to minimize I/O, the design goal of a T tree is to minimize memory use. Hash tables can quickly locate a single unique index entry. Hash indexes can be faster and use less memory than either of the types of tree indexes. And then custom indexes are B trees that allow the application to define the collating sequence or the sort order of the entries rather than defaulting to a simple lexicographical or numerical sorting. And we'll look at a couple of examples of where being able to control that comparison function could be useful. As I said, the B tree is the most popular data structure used in database and file systems. The main idea behind the B tree index is to reduce the number of disk operations that are needed to add, find, or remove a data element. By definition, a B tree of order M is a tree where each node may have up to M children, and it's usually called an M-way tree, in which A, the number of the indexes in each non-leaf node is one less than the number of its children, and these keys partition the children's keys in the fashion of a search tree. All the leaves are on the same level, and all non-leaf nodes except the root have at least M divided by 2 children. And B, the root is either a leaf node or it has from 2 to M children. And finally, C, a leaf node contains no more than M minus 1 keys. Each B tree page contains a reference to a child B tree node, the key value, and a pointer to the data associated with the key. Some variations, such as the B plus tree, keep all records only on leaf pages. Entries on a B tree page are ordered by the key value, so binary search is used to quickly locate the requested element on a given page. Search and traversal of B trees is straightforward. Using left to right, depth first traversal, the algorithm gets all elements of the B tree in sorted order. Insert and remove operations are more complex since they require rebalancing of the B tree. The tree is structured so that ideally at least half the available space on each of the internal pages should be used. In case of underflow, in other words to an empty page, or overflow, the page can't hold all the elements, then elements are redistributed to neighboring pages. If such pages don't already exist, they're created or, as the case may be, merged together. In order to perform a lookup without accessing the data records themselves, a B tree needs to store the search key value on its pages. This is one of the disadvantages of the B tree. All the keys are stored twice. The key is stored in the record itself, and it's stored again in the index. It also means that the maximum size of the key is limited by the size of the B tree page. or more particularly, the size of a slot within the B-tree page. Incidentally, this feature, the ability to perform a key lookup without accessing the data records themselves, in database terminology is called a covered query. And you can go Google covered query and read all about that. I'm not going to spend any more time on it here, but it's an important concept in database systems. A B-tree is always maintained to be balanced. A balanced tree is a tree where all the internal nodes are at the same depth and of a small height. Each operation with a B-tree requires access to no more levels than the tree is high. Therefore, insert, remove, and find operations have logarithmic complexity. In order to reduce the tree height, the B-tree pages or nodes are large and are often mapped to the database or file system page size. In other words, if the blocking factor on your file system is 4K, then your database page size is also likely to be 4K, and so your B-tree node size will be 4K. And I'm going to use the term B-tree page and B-tree node interchangeably. They're really the same thing. So let's walk through what I've just covered. Here's an example of a B-tree. In this case, it's a B-tree of order 5. In other words, M is 5, containing 26 items. The number of keys on a non-leaf node is 1 less than the number of its children. All the leaf nodes are on the same level. Non-leaf nodes, except for the root, have at least M divided by 2 children. A leaf contains no more than M minus 1 keys. When searching data held on disk, the cost of each disk transfer is high, but it doesn't really depend very much on the amount of data being transferred. That's especially true when consecutive data items are transferred. So what I mean is, it costs about the same to transfer 4K bytes from the disk as it costs to transfer 100 bytes from the disk. B-tree nodes, again, using that term interchangeably with pages, are usually stored as database pages or file system pages. The node size is usually equal to the size of the database page or the file system block. So these pages can be loaded into memory and read all at once. So the disk is always going to do I/O in terms of whatever its blocking factor is. So again, if the block size is 4K, it's always going to read and write 4K, even if you only want 100 bytes. The disk is always going to read 4K. So for example, with a typical B-tree page size of 4K, each page is able to hold up to 512 entries that have an integer key value. So indexing 100 million records requires a tree with a height of only 3. This in turn means that an index search of 100 million records requires at most 3 page reads, and usually even less, since the root is almost always going to be cached in memory, and then some of the values are going to be found on the second level pages, so that you don't have to go to the bottom level of the tree, to the third level. The B-tree allows processing of common SQL queries, for example, those that we see on this slide. In other words, using a B-tree, applications can efficiently locate records with any range of key values, and the range boundaries can be open, in other words, not specified, or it can be exclusive or inclusive. In addition, once the lookup is complete, the B-tree allows iteration through the records in the desired order. For example, the following query doesn't require any further explicit sorting provided that there's an index for the age field, that query being select star from person order by age. The application just iterates through the records by age in increasing or decreasing order depending on the direction of iteration. When all your data is stored in RAM, in other words, not just cached in RAM, but then stored permanently on disk, the B-tree index design goals are no longer a good match. Since we never have to go to disk with an all-in-memory database, we don't care about minimizing disk accesses. At the same time, we do want to minimize memory consumption. So this, coupled with the fact that we don't care about minimizing disk access, eliminates the justification for keeping a redundant copy of the indexed data in the index structure itself. To save memory, we can store a pointer to the indexed data, and following a pointer in memory is very inexpensive compared to following a pointer on the disk, which requires another disk access. There are two pleasant byproducts of this. The pointer to the data that is inherent in the B-tree algorithm can be reused, and we gain greater simplicity by virtue of not having to deal with variable length data within the slots of the index nodes. Variable length data, for example, being a variable length string that's being indexed. And that's exactly what we do within ExtremeDB. We've modified the standard B-tree algorithm so that we don't store that redundant data within the index slot. That keeps our B-tree smaller, so we save memory. Also allows us to store more slots on a given B-tree page, which keeps the tree shallower. So there's a lot of benefits to not storing that redundant data within the index slot itself, but that's only a good strategy for an all-in-memory database. In addition to modifying the B-tree structure, there's a couple of other memory index structures that can be used efficiently to index objects in main memory, and they include the binary tree, or ABL tree, which is named for its two co-inventors, Adelson, Velsky, and Landis. However, as main memory is often limited in size, then measures have to be taken to minimize the space used by the index so that we can fit all the data in memory, which presents one of the main challenges for in-memory search structures. So again, there's two types of index structures that are well suited for all in-memory data. Those that randomize the data, and hashing is the primary example here, where there's chained bucket hashing, linear hashing, and extendable hashing, and those that preserve the natural order of the data, such as arrays, binary trees, B-trees, and the T-tree structure that evolved from ABL trees and B-trees. As opposed to the standard B-tree, the T-tree design goal is to minimize memory overhead.